Okay, well, good afternoon. Hope you all had a good 1 hour lunchtime. Okay, so the plan for today, we're going to start with, as always, a recap of last lecture. We're then going to move on to what we discussed for the last part of last lecture, a two-dimensional triangular shape function. So a few of you commented on the online form that I went through this quite quickly, and generally this is the problem of kind of covering some of the material from before, is we end up not having too much time at the end, but hopefully most of you had a chance to look at the reading, which included that step by step, and hopefully when we go through it today it will make a lot more sense. We'll then talk about how we solve the equation in two dimensions. So this here is the differential equation we'll aim to get to the point of solving by the end of today. Now, hopefully, because we've gone through the one-dimensional case several times, this should all seem very, very familiar. All the various steps should at least look similar, and hopefully you understand that the big difference here is it's just more mathematics. We've had a chance this morning to play around with some of the Matlab, so again, hopefully that's starting to make sense. A few people asked me about maybe doing some extra Matlab courses. Now, definitely within the room, I think there was a wide range of background and experience. So one possibility is I could maybe do 20 minutes for people who need a bit more Matlab at one end of the room. We have a projector which is fairly rubbish in that room, but I could try to at least cover some of the basic concepts. So for the QR code, if you start giving me some ideas of what you'd like me to cover, I could try to at least give you some kind of extra bits on that. And then everyone else can work on their assessment or the exercise we talked about today. Probably today we're not going to get to the constant and the Helmholtz term in two dimensions. That'll be for next week. But you know, in principle, everything we talk about here is kind of similar to one dimension. So hopefully by showing you what we do in two dimensions, this should click, and you should see the extension to two dimensions is not too bad. So understand what two differential equations are, and I'll cover that again. I'll introduce the mathematics of the triangular element, and again, this is like the one-dimensional case, but with just more mathematics. And then we'll talk about the process of solving. And again, this is the same process of forming it into a matrix that we can solve in Matlab. So we're now week 6. We had the lab this morning and the lecture this afternoon. Next week it's exactly the same. And then for week 7 onwards, we'll be having just the labs in the afternoon in this slot. But you have all of that on your timetable. Okay, so I'm sure you're familiar with the system, at least those of you who are coming to the lectures, but basically we have this QR code in the corner. If you can do at least once per lecture, just register to show your attendance here. And then any point during the lecture, please, any comments, any criticisms, anything that's not clear, please put on there. And I'll try to cover them. Okay, so I have to apologise to people who put comments from lecture 3. I think they must have put them in after the actual lecture because I actually missed them before. So there's a couple of things I wanted to just cover here that I think I must have missed from lecture 3. Hopefully it's not too late and those questions are still kind of relevant. But just to start with some of the positives, I think people were quite happy with the fact I did a refresh of last lecture. I'll keep trying to do that. And then a mixture of slide and board notes. And then there were, at least one person was quite happy on the poll EV, poll everywhere question. So again, I'll try to do a few of those today. But again, obviously, if you disagree with these, please feedback. So then the kind of concerns or criticisms, again, too quick at the end, which is usually because by the end I'm trying to introduce a concept that, you know, ideally motivates you to read in between. So obviously we don't cover it in full detail and then try to cover it the next time. And again, people saying the calculations are shown too fast. So again, please if you could put a little bit more detail exactly which calculation's too slow, which bit you're kind of lost on, and then I'll try to avoid writing green. I'm sorry, that's kind of my fault with that. Green is a bad colour, so I'll avoid green as far as possible. Okay, so a couple of kind of clear questions here. So one of which was, I was a bit lost when you subbed in x minus x1 here. So this part here, I assume what was meant by this, and it's difficult to know without a bit more detail. So if someone could put in a kind of bit more detail on this, exactly what you meant. But this is essentially the form of the shape function, and it occurs in various places. So you remember we have the kind of form of the shape function element of x, and that's equal to n1, say, times u1 plus n2 u2. Now the reason you get this x1 minus x2 over h is when we do the derivative of this, and I assume this is what's meant here. And again, please, kind of a bit more context if possible, but we end up with a form that's u2 minus u1 over h. And the way we get this is actually by taking the derivatives of each of these n terms. So these n terms individually, for example, n1 is equal to x2 minus x over h. So the derivative of this, dn1 by dx, equals minus 1 over h. Same process for n2. So dn2 by dx ends up giving us 1 over h. And then we substitute those into this expression for the derivative, and we end up with this. So that's one particular case that could happen. The other one is the integral over trapezium rule. So we've covered this several times, but if this still doesn't make sense, please go back to watch lecture 2. And there's an extra derivation there where I actually went through that in detail, and if it's still not clear, please come and talk to me. The other thing that people had is the pole everywhere result. Generally, people didn't get this expression here for the shape functions in terms of eta. So you remember we had these shape functions that were 1 minus eta over 2? And the idea was to equate that shape function, 1 over x, to n1 equals that, and then the expression we should have got was something in the form of dx by d eta. And that should have been an expression of h over 2. But generally, I think most people didn't get that correct. So if you can go back to that expression and just make sure that you understand exactly what we have there, and why we get that particular expression, and understand the concept of that as a mapping. And then this question here, which I think is probably one of the kind of key questions of this process, and it's one of the things that I think is most counterintuitive in this process. So what I'll do is I'll just try to give you a bit more context for that. So the way to think of these weighting functions is it's kind of like a scaffold. You build up a scaffold essentially in order to build a building. So you have some scaffolding, and you essentially use it and you build up some building, and then after it, once you finish with it, you can get rid of the scaffolding. Now the reason this is like a scaffold is the key points of scaffolding is that they essentially are there for the purpose of building the building, so they're essential for the building, but once you build the building, you no longer need them. And then the other key point about the scaffolding is we can choose them to be exactly what we want. They don't have to be beautiful, they have to just be basically functional. So can be anything we want. So just to give you a kind of example of how this would work, I'm going to choose an example that's kind of trivial, where let's say we take the function f dx. So f is just a constant. This is the force term, and we're multiplying it by this omega term. That's the essentially the expression for the weighting function. Now the reason we get an expression like this is it's a least squares fit. So we're integrating, this where the omega is like a weighting function. It gets us as close as possible for our linear solution to the true solution. So you think about this picture we've seen a few times where we've got a linear solution fitting to that. So we work through the mathematics with this, and this would be a function that would be equal to 0. We'd work through the mathematics for this, so we basically integrate this expression, and we'd end up with something along the lines of omega 2 minus omega 1 times hf over 2. So this is essentially working through and doing trapezium rules. So don't worry too much about the details of this. You've seen this before. For a constant, this is the expression you get. The key thing I want you to understand about this is we now have these weighting functions. Now, there are various ways that this equation can be true. One trivial way is that omega 2 minus omega 1 is equal to 0. Now, if that's true, then this equation is equal to 0. Another way this equation could be true is hf over 2 is equal to 0. So if this is 0, this whole expression equals 0. If this is 0, this expression equals 0. Now, the key point about the scaffolding here is we choose this so these expressions are never equal to 0. So we actually say that omega 1 is not equal to omega 2, which would make this 0, and is not equal to 0. So we choose our scaffolding to be exactly what we want. So what this means, the other thing about this expression is this is trivial. This expression is not what we want. If you think about our aim is also to get an expression that's valid at each of these nodes, node 1 and node 2, where omega 1 and omega 2 correspond to the weightings at those nodes. If this is true, if this is equal to 0 in general, then this is not satisfying both nodes. So the whole point of this is we essentially want something that is valid for both nodes, and also, we choose our weighting function so this doesn't happen. So essentially what we end up with is two separate equations that have to be true. Omega 2 and omega 1, hf over 2 is equal to 0, and hf over 2 is equal to 0. So we end up with two separate expressions that have to be true, and this is the same as saying that both nodes have to be satisfied. Sorry, there's a minus sign here. What's important about this is that because we know omega 1 and 2 are not equal to 0, we can basically move them over to this side, divide both sides by that, and essentially we end up with just two separate simultaneous equations that no longer include those expressions. Does that make sense? It's sort of clearer, less clear? So that's essentially the logic there, is you're kind of using them like a scaffolding, and then at the end, once you've used it for what you need, you can get rid of it, and essentially the building stands by itself. You have an expression that then is valid and is the minimal least squares solution to your differential equation, essentially. Okay, so please let me know if that didn't make sense. I'll try to explain again next week. We have some time next week to kind of cover just general bits and pieces. Okay, so these were the plans for the last 3 lectures. We're now on lecture 5, and we're moving to 2 dimensions, solving with Matlab, boundary condition, numerics, and forming arrays. Okay, so we'll start again with this definition of a derivative, and this is the kind of starting point for this entire process of continuum mechanics. We essentially define a derivative, which is the limiting case, a gradient, as we zoom in to the point when x, delta x, that difference, that gradient of the line is equal to 0, and we define this derivative. That is, a mathematical placeholder. It's something you can never actually get to, but it's essentially useful mathematically because it allows us to define differential equations. Now, over the last 4 lectures, we've looked at the effect of each term in this equation. So this is the equation with a second derivative term. What I've called the Helmholtz term, the plus t, is equal to f. And we've looked at how we solve each part of these equations, lecture by lecture. So for the first lecture, we essentially solved that directly, and you can see that's a linear solution. And hopefully in the Matlab tutorials today, you started to play around with this and understand the various forms. For the forced term, we get the parabolic profile. And then for this expression here, and this is the case where we've actually included this arbitrary coefficient lambda here, we actually get the kind of sinusoidal or cosinusoidal solution of that. So just to kind of give you an idea physically what these correspond to, first of all, if you think about the equation we'll solve in the assessment, you can see it includes all of these terms: Helmholtz, forcing, and diffusion. So when you come to do your assessment, you should be talking about this equation physically in terms of what these terms mean and what they do. And understanding essentially, physically what you should be getting in terms of solutions when various terms are 0 or not. Now for the computational fluid dynamics, this is the Navier-Stokes equation. So just to give you this is an example of turbulence on the left-hand side, which requires both this unsteady and convective term. For the case where we haven't got either of these, we can think of the forced, so this pressure gradient essentially becomes like a forcing term, plus some viscosity, du by dx is equal to 0. So this was the equation we solved, and this you can think of physically as being a channel with a parabolic velocity profile. We also then have the case where there's no pressure gradient, and we just solve du by dx is equal to 0, And this is the case where we have, say, a sliding top wall and fixed bottom wall, and this is where we get what's called Coet flow, which is a linear velocity profile. So both of these kind of physically correspond to cases you see in fluid dynamics. And one of the things you can do with the examples in Matlab is actually combine both of these together. and get a solution where you would actually have, you know, pressure gradient and sliding walls. And, you know, you could think of this being the gap between a car, for example, and a road. So if you had a car on the road, you'd essentially think of the pressure from the flow going into it, and then also the actual movement of the car itself, and you get this kind of compound solution that essentially you can now model with these differential equations. For solid mechanics, one of the things you can do is if you have zero acceleration for this term, you can actually rewrite the stresses in terms of coefficients, Lamé coefficients, and write an expression for, you know, a test piece here. So you can think of cases where you're, say, stretching a test piece, and you could imagine plotting the extension, you know, as being a linear solution based on that. Or the case maybe where you've got some form of pinned beam and you're bending it in this way. I'm not going to emphasize this too much because generally the sort of moments in beam equations you get end up being more complicated, but, you know, physically hopefully you can at least see that, you know, these terms here correspond to the stresses, and you have the kind of body forces. And then this was an example in the bottom right of a material that's anisotropic. So those kind of coefficients inside the matrix vary through the material, and that's going to be the case for your assessment exercise. Now, one of the other things you can do with the solid mechanics equations is rewrite them in terms of an acceleration and a waveform, and this ends up giving you the Helmholtz term that we've seen before. So on the left we have guitar strings, and you can see, you know, you get these wave solutions that we hopefully started seeing in the Matlab tutorials if you've got that far. If not, they're kind of on there if you want to have a look. And you can see the kind of number of modes you see depends on lambda. So this is one of the solutions for that. And then obviously for engineering context, it's the most famous example of that being a problem is resonance in this bridge that ended up breaking itself apart. For electromagnetics, we talked about this. So that solving these equations in general will give you an electric motor, but you can also rewrite them as a wave equation. And then this is important for propagation of radio waves and telecommunication style problems. And, you know, hopefully it's a little bit of a different form here, but you can see this is actually the form of Helmholtz equation, but this would be a form of lambda E on this side here. Yeah, and finally for the heat transfer case. So on the right is the kind of full heat transfer equation. You can see all of this complexity, this flow, this effect of kind of burning. But, you know, the simple example is a heated beam. And you can imagine if you've got a beam, fixed kind of temperature at both ends, and you heat underneath it here, what you would see is a spread of temperature like this, and you get a kind of parabolic profile. So you can think of that almost as being like a heating source term. Or similarly, if you heated just one end, like in this example here, you'd see a linear transfer of heat. And you get the straight line solution that we've seen before. Okay, so all of these come from these differential equations. All of these come from solving these kind of derivatives that describe physical phenomena. And the whole point of finite element analysis is to approximate those as a series of straight lines. So we're basically just approximating our solution as a load of straight elements, putting them all together and getting an approximation for our solution, which is nice because a mathematical limiting case can never be obtained. So you've seen this a few times. The idea here is our function ux, and we're approximating using u element with our shape functions. And then just the syntax here, we have the node numbers being kind of the points where the elements meet here, and then the element numbers being the ones in circles. Okay, so then the next thing to note is just the form of this equation. And this is the way you'll see it written in most textbooks, is that we actually end up writing an expression like this is equal to f, and we define this to be a. So you can see this is a form of at is equal to f. So we're always solving equations in the form of au minus f is equal to 0, and then we're approximating our u, or in this case t, function to be, you know, the u expression for each of those elements. So we're solving exactly the same equation, but instead of using a continuous function, we're using a series of straight lines. We then fit those series of straight lines using a least squares process. So we're getting the closest approximation to our underlying equations from a series of straight lines by optimizing the weighting functions and making them as small as possible to get the best possible approximation. So that's the entire purpose of the finite element process. So for this equation with 3 terms, the process is always the same. We use integration by parts to rewrite the second order terms to first order terms plus a surface term. And this is in order to make it easier to solve. And also give it this nice property that the surface terms cancel. And this was done in lecture 1. And the key point of this is that these derivatives are basically constant functions, as we've seen. Because we've got a straight line, the derivative is just a constant. For lecture 2, we looked at the effect of replacing the forcing term, and that was basically just the expression that ends up being the integral of this, which we integrate using the trapezium rule. So that term we have as a trapezium rule style term. And then the last thing we looked at last week is this Helmholtz term, which is more complicated because it's a product of two shape functions. The product of those two shape functions I showed you are easier to solve by writing in a different coordinate system. So that was using these coordinates where instead of n1 as a function of x, we actually mapped it to n1 as a function of eta, which is equal to 1 minus eta over 2. Now in multiple dimensions this becomes far more important. In other words, we go from a very complicated shape to one that's much easier to solve. And then we collect the simultaneous equations for each node, put them in a matrix and solve them. So it's just solving loads of simultaneous equations for each of our straight lines. Okay, so this process I'll just show you very briefly. You've seen this before. This was for 3 elements, and hopefully by going through the Matlab today you're starting to get an idea physically how this works, but each of these is an expression for each of the elements. So this is element 1 here. We add that to element 2 and element 3. The position in the matrix is just to do with which coefficients it's multiplying. So this one is for 1 and 2, for example. We collect them all together, and then we can solve that. Now on the right-hand side, we have the fluxes. Now these are the expressions for the surface term that we get from that integration by parts. And the key thing to understand here is that these surface flux terms, when they meet at a node, they're the same value and they cancel out. So what this basically gives us for this formulation is we're actually rewriting in this form, and all of the internal fluxes cancel because it's a continuous function. So what we end up with is a function entirely defined by just the fluxes at the two ends, or the boundary conditions. And as I said before, physically this makes sense because your entire system is defined just by those boundary conditions. When you solve those first order differential equations or second order differential equations, you had to put in 2 coefficients, 2 unknown boundary conditions. Exactly the same process here. We discretize the whole system. You'd expect only to need to know 2 values, the values at the end that determine the problem. Okay, so hopefully that all makes sense, and the idea is we're going to do exactly the same thing in 2 dimensions. So in 2 dimensions we now have functions that are of 2 variables, x and y. Now this is, you can think of a kind of contour plot as like looking down on a hill. So the colour represents the height at different points, and then x and y are the axes. I haven't labelled them, but x and y here. And this is just an example of a polynomial. And one of the exercises that I encourage you to look at, that you had today, was to actually look at different coefficients and look at how that surface changes. It's well worth doing to understand exactly how a 2-dimensional field works, just kind of conceptually. And then the whole point of this is then we define derivatives on this surface. So in the same way, in 1 dimensions we have a curve and we take the limiting case of a gradient. In this example we basically make this box smaller and smaller and smaller until it's kind of a point in space and gives you the gradient at that point. In order to do that we have to do partial derivatives, and the key point about partial derivatives is that we're holding either x or y constant and differentiating with respect to the other value. So you can think of these as being kind of derivatives along lines of constant x or y, which there was last week. We talked about how we do that for that. Okay, so in terms of these partial derivatives, we now have what's called a partial differential equation. And the rest of today I'm going to talk about how we solve this partial differential equation in 2 dimensions. So notice it's a function of 2 variables, so this is diffusion in two dimensions. And you can think of this essentially like being a drop in water spreading outwards in 2 directions, rather than just in one. So the process is exactly the same. We essentially form an A matrix here, where d by dx squared, so d2x, plus d2 by dy squared times t is equal to 0. So you can see our A matrix this time is essentially this, and then the form of the equation is identical. So again, the process we used again is exactly the same. We basically replace t, the continuous function, which in this case is now a continuous surface or field, depending on how you want to think about that, with a series of approximations. Now in 2 dimensions we can't use straight lines. The simplest, or one of the simplest, is to use triangles in this case. So we're describing our surface as a series of triangles here, and you can see this being a kind of good approximation. And this is what's done in film graphics and all sorts of things as a kind of triangular mesh. So this is kind of commonly used. And so the process now is one of least squares. So we're doing a best fit of the triangular surface, minimizing those weighting functions as we did in 1 dimension, now to fit this kind of approximation to the surface in 2 dimensions. A couple of things to note here is this integral now is over 2 dimensions. this omega is kind of general integral. So before we were integrating just over the one-dimensional linear case, now we're integrating over 2 dimensions and fitting that surface to that expression. Okay, so now the idea is we're going to go through exactly the same process. So the steps are exactly the same. Firstly, we use integration by parts to re-express our equation as first order terms. We then replace the t and omega terms by triangular approximations. So this is the key difference here, is that we're no longer using the linear approximation with just n1 and n2, but using the extra term with n3. And then we collect together the simultaneous equations, put them in a giant matrix, solve them as a series of differential equations. Okay, so I'm going to just show you that process again that we went through at the end of last week. My computer works. Is that sideways for you as well? Okay. Okay, so the process of defining an element. So before, you remember we did it in 1 dimensions. We basically had the 2 expressions at the end, u1 and u2, and we used that to define an expression for a straight line. The process is exactly the same, but for a triangle this time. So let's take a triangle, some arbitrary triangle, and it can be any triangle. We have the coefficients, the points u1 and u2, so x1 and y1, x2, y2, and x3, y3. And the idea is we want to define this u element as a function of x and y that describes this triangular element. So u element of x, y, what we're going to do is we're going to substitute in the values for u of x1, x2. Sorry. U is equal to, so we're going to say u1 is equal to u at x1 and x2. And that's equal to, let me 1 second actually, sorry. So the form of the element equation that we want is going to be of the form alpha 1 plus alpha 2 times x plus alpha 3 times y. So just to explain this form of the equation, you can think of this as being a constant point, and then this term that varies in x and this term that varies in y. And this is kind of the simplest function that will describe a triangle element, essentially. So it has the x dependence, the y dependence. And the trick now is we need to work out what the coefficients alpha 1, alpha 2, and alpha 3 are that actually define this element. So the process is going to be essentially what we did with the straight line, where we substitute in the known values. So we have alpha 1 plus alpha 2 times x1 plus alpha 3 times y1. Sorry. And then for u2, that's going to be equal to u2 y2. So I'm making all sorts of mistakes here. It should be 1. Okay. Alpha 1 plus alpha 2 times x2 plus alpha 3 times y2. And then finally for u3 is equal to u at x3, y3 is equal to alpha 1 plus alpha 2 x3 plus alpha 3 y3. So all I've done is substitute in the 3 corners, the known values at those corners, into this general function for an element here. Okay, so now the process is to solve in order to get the alpha 1, alpha 2, and alpha 3 values. So the way we do this is to assemble it into a matrix. It's not the only way we could do this. We could solve these simultaneous equations by hand. It's going to end up being much more tedious. So the easiest way is to actually do it as a matrix, and hopefully after doing a bit of Matlab, you're kind of getting used to thinking in this way. So the matrix you can see is going to be of the form y2, y3, all times the alpha 1, alpha 2, and alpha 3 coefficients. So that's just an expression of the simultaneous equations essentially in matrix form. So this is matrix U, and that's equal to the coefficient matrix there times alpha. So now, in order to get alpha, we need to invert the matrix C to the -1 and multiply it by U in order to get the values for alpha. Okay, so the process of inverting C, and as I said last week, no one should have to invert a matrix by hand. And I showed you before, if we go through, This process here. So these are the coefficients that we actually want to get, and the idea here is we're going to solve for alpha. The process of inverting a matrix. So you essentially go through to get the inverse of the matrix. You take the transpose of the matrix. You then get the determinant of the matrix, which is a fairly tedious process of going through, getting the matrix of cofactors, multiplying each of them together, and assembling together all of the terms. Now, if you work through that process, you get this matrix here. The alternative is to go to something like Wolfram Alpha, or for those of you who did the second part of the Matlab first tutorial that you weren't meant to do, actually you've got an advantage now, because there's actually a symbolic manipulation. You could actually use that to solve this matrix. So if you looked at that symbolic part, this could actually be used in that part to invert a matrix of symbols and actually get an expression. But the key point here is that it's essentially just algebra. You essentially work through the process for all of this, and you end up with this matrix of all of these different coefficients here. So once you've done that, the next step is to actually recognize what each of these terms are. Now, what we can see is actually each of the expressions in that matrix. Let's go back, sorry. So each of these expressions in the matrix, you can see the first row here are actually the three parts that, if we add them together, give us the area of the matrix. Now, for this area of the matrix here, you can actually show this, the determinant, using trapezium rule, by taking each of these different parts of the triangle, working out the area here, and then if you do the last part, you get the area here. If you work through that process, you can actually see that it will give you the same expression as you've got here for the determinant. So that expression is consistent with basically doing that process. So if you want to convince yourself the determinant is actually the area of the triangle, then that's possible to do. You could also think of this conceptually. If you actually think of like the simplest possible triangle, the actual matrix that defines this triangle you can see as essentially being like a skewing of a parallelogram. So there's a kind of argument along those lines, but you can just trust me that this is actually the area underneath here. Now these top three terms, if you add those together, they will actually give you this expression here. So the sum of these three terms here give you this. So these top three terms we can call A1, A2 and A3, capital A. They're the contributions to area. Now each of these terms in the lower rows are essentially the distance between the top and bottom of the triangle. And this is shown here as the various red lines here. So for example, A3 is the line between 1 and 2. So the index of each of these is always the third index based on the other two, if you like. And you can see the kind of general relationship. AI is AK plus AJ. And this table here gives you the kind of indices you should use. So essentially this process we can actually substitute in, and it gives us the inverse of the matrix in terms of these three area components, and then these expressions that are basically the distance in X and Y of the points, the vertices of the triangle. Okay, so why is this interesting? Well, now we've got this expression. In terms of this, we can basically multiply this out in order to get the expressions for alpha 1, alpha 2 and alpha 3. And then we can actually get the form of the equation in terms of the shape functions n1, n2 and n3. And so this is the shape function that you've been using in 1 dimensions, now in 2 dimensions. So this is where you have to do something. The idea here is to multiply this matrix out, collect the terms together, and get the form of n1, m2 and n3. So essentially, the process essentially of solving and working out what this expression for the element matrix is. If you bear me 1 second, just set up the poll level. Okay, I'll give you about 15, maybe 15 minutes for this. And it's the same link, I think it stays the same link actually between the one you had before, so it's Edward Smith 152, for those of you who did it before. So I've copied the slide here, so hopefully you can see that, and then basically the expression for that. And for those of you who are wondering where the slides are on that, the reason I haven't put them on there is so that you can't cheat and look at the next slide. I will upload them after the lecture. Does that make sense? Anyone unclear? So, okay, can you read this on your phone? Or whatever you're using to look at Poll Everywhere? Is it readable or too small? That's a bit small on there, isn't it? anyone completely lost or any help? So I think it's possible for you to change your answer on this, right? So you can put in an answer and then you can change it later on. Is that right? So maybe we should do it where you kind of have a first guess and see what the initial guess, and then change it later on. Okay, a couple more minutes and then I'll work through. Okay, so let's have a quick look at the responses. Okay, brilliant. So the majority of you have got this. This was also a test to see who'd actually look through the material between last lecture, because it was actually on there, the answer for that. But hopefully most of you at least worked through it and understood the process here. So it is just algebra. It's very much just a process of working through, but it's well worth doing to make sure you understand. So let me take this. I can paste this? Yeah, brilliant. Okay, so the process essentially is just multiplying out the various parts of this. So we essentially multiply out, take 1 over 2a outside, and we're going to multiply out the various terms in the matrix. So for alpha 1, so for alpha 1 we're just going to multiply out each of the terms, 1 over 2a, and it'd be a1 times u1 plus a2 times u2 plus a3 times u3. So just matrix multiplication. For alpha 2, it's equal to 1 over 2a, and we just multiply out the terms again. So this is b1 times u1 plus b2 times u2 plus b3 times u3. And for alpha 3, 1 over 2a, a1 times u1 plus a2 times u2 plus a3 times u3. Okay, so then the process is we want to stick it into the original equation for u as a function of element, which is a function of x and y, which is equal to a1, alpha 1 plus alpha 2 times x plus alpha 3 times y. So this is the general equation for any triangle, and we're just going to stick in these expressions here for the 3 coefficients. So let's just first of all start by taking out the common factor of 2a out of everything. So what we end up with is a1 u1 plus a2 u2 plus a3 u3 plus b1 u1 plus b2 u2 plus ... etc. So essentially each of those terms. Now the next step is going to collect together the terms for u1, u2 and u3. So we have a1 plus b1 plus a1 there times u1. Bear with me 1 second, sorry. You're being a bit too hasty here. So that the key point here is that this is multiplied by x. A2 u2 plus a3 u3 is multiplied by y. So that's my punishment for not writing it all out. So then we're collecting together the terms in u1, u2 and u3. So we end up with x times this and y times that. Yeah, sorry. Should probably move that over there. So each of these terms, so each of these terms, this expression here is alpha 2, this is alpha 3 times by y, and then what we're doing is we're collecting together, it would help if I turn that. So we're collecting together the terms in u1, and then we have alpha 2 plus b2x plus a2y times u2 plus a3 plus b3x plus a3y. So this process is identical to what we did with the straight lines. You know, we basically worked through the mathematics, we derived an equation for a straight line, we substituted in those expressions, and then we collected together these terms. So this term here is the expression. I'm going to just move this inside just so we're consistent. So this is over 2a, this is over 2a, and this is over 2a. These terms here we just call n1, n2, and n3. That makes sense. And these now contain all of the xy dependence of our functions. So we end up, and this is the entire purpose of doing this process. It's an approximation, and it's called a constant strain triangle for reasons I'll show you in a sec. But essentially, all of the xy dependence are now contained in these shape functions, these ny, n1, n2, and n3. So the last thing I want to show you, and then we'll have a quick break for maybe 10 minutes, is taking the derivative of these. So if we do du by dx, now bear in mind this is the partial derivative. So what we're doing is we're keeping y constant. So this is taking only the x derivative of each of these terms, and that gives us d n1x u1 plus d n2x times u2 d n3x times u3. And if you look at these expressions for n1, n2 and n3, there's only one term that's a function of x in there. We're holding y constant, so that disappears when we take the derivative. So this entire expression just becomes b1, this becomes b2, and this becomes b3. So we end up with b1 u1 plus b2 u2 plus b3 u3. So this is why it's called the constant strain triangle. The derivative of the expression is a constant. So if you remember before when we talked about fluxes and the values themselves, the derivative of displacement is strain. Derivative of temperature is heat flux, for example. So these could be called the constant heat flux triangles. But the key point here is there is actually no x or y dependence anymore in this derivative. And this makes the mathematics much, much simpler when it comes to kind of more complicated examples. Okay, so the same process worked through for the derivative with respect to y, with x held constant, gives you an expression for a basically for the element in terms of again constants, but this time the constants a1 u1, a2 u2, and a3 u3. Okay, so about to take a break, but I'll just show you quickly why this is all relevant. So essentially, this process we've just done, we get the expressions for n1, n2 and n3, and remember the notes I gave you last week do all of this in gory detail step by step. And then we have these derivatives that essentially give us the expressions in terms of the constants, b1, b2 and b3. And so the key point now, and this is what we're going to do in the next part of the lecture, is to insert these expressions in terms of these constants into the inside of this bracket here. If you remember before, the reason we did this for a straight line is because the derivatives were constant, and this makes the integral over that line very simple, and it's going to be the same for a triangle here. Because these expressions are constant, it makes this integral of this much, much simpler. So what I'll show you when we come back from the break is that process, and the process of inserting the triangular approximations and then collecting together a set of simultaneous equations to solve, to give you the finite element solution of the differential equation. Yeah, we'll start again at 10 past. Hey, yes, yeah, please.
You are reaching
Sorry, the document is...
I don't know the notes that you are reading at the moment.
Yeah, definitely. I mean...
Because last week we didn't...
I did by Friday, so they were late on there. Oh, you mean the actual notepad? Did I not put those on there?
The notepad that you are...
Oh, sorry, yeah, I can do that, definitely. Sorry, yeah. Yeah, absolutely. So I think we're recording. Yes, perfect. So the next thing I want to show you is basically how we now go about solving a two-dimensional version of this equation. So essentially the process is going to be one of substituting in these expressions for the derivative of the element and then working through the mathematics in an identical manner to the way we've seen before. So we've got an expression where we're solving d omega by dx dt by dx plus d omega dy dt dy, and this is all integrated over this volume. Is this okay? Does this make sense? Everyone knows where this comes from. We also have a surface term here. So this is what we get from integration by parts in 2 dimensions. Yeah, just for completeness, I should actually say that the starting equation we're solving, d2t by dx squared plus d2t by dy squared, d omega. And then what we do is we actually use essentially integration by parts. Now in 2 dimensions, this is a slightly more general version of that, called Divergence Theorem. Now physically, you can think of this as being an expression that says, basically we can rewrite a derivative as the fluxes over the surface and the changes internally. So this is kind of consistent with the physical interpretation we've talked about in 1 dimensions. And we'll come back to the surface terms a bit later on, but the key point here is that it's the same process of rewriting a second derivative as first derivatives essentially. Okay, so then the expression for, say, omega as an element dx is equal to 1 over 2a, and this is the x component, so it's b1 u1. Let me get my notes just so I don't make a mistake. Yes, so dx is b1 u1 plus b2 u2 plus b3 u3. So this should be w, of course. w3. Similarly, if we do the same thing for dt element dx, that's equal to 1 over 2a b1 t1 plus b2 t2 plus b3 t3. Okay, does that make sense? Now one thing I want to just highlight is a way of writing this. Now we've started to work with Matlab, and you've seen in Matlab you start to think in terms of matrices and products of matrices. So we can actually rewrite this expression here without changing it at all as 2 matrices. So essentially that's exactly the same expression, just rewritten it as a matrix. Hopefully that seems reasonable. Anyone outraged by that? Or okay. So perfectly, and then we can do the same thing here. T2, T3, and B1, B2, B3 like this. Okay, so let's get rid of this. Okay, so now we're going to take the first expression here. Call that 1, call that 2. So 1 is just dt epsilon by dx times d omega epsilon. Sorry, I keep calling this omega. This is w or omega. The reason I keep calling it omega is basically a slightly squiggly w in a lowercase. So w or omega I use interchangeably. So then this becomes essentially the product of 1 over 2a w. Let me do it in the order I did it. So this is going to be w first, t first. So w1, w2, w3, b1, b2, b3, t1, t2, t3. This is b1, b2, b3. Okay, so we just literally substitute in the expressions for these two. We needed another 1 over 2a here. Okay, so that gives us 1 over 4a squared times w1, w2, w3. Now what we're going to do is we're going to collect together the two B matrices and multiply them out. So what we end up with is the product of these two matrices. So we do this element by element, essentially like an outer product. And this gives us every permutation of these two matrices. B3, times T1, T2, T3. So this, what we've done here is essentially like an outer product. If you're used to using index notation, you can think of BI as being B1, B2, B3. So then BI times BJ is going to be this product, essentially, and then you can do I and J can be all three values. So this gives you a kind of product of those. The other way this is sometimes written is a kind of outer product. But essentially, it's the consequence of rewriting in this form. In matrix form, you can think of this as omega matrix dotted with the B matrix, if you like. Transpose. I think that's right. So now we have this expression here. Now the process for d omega dy, dt dy proceeds in exactly the same way. We end up with exactly the same set of expressions, but this matrix now is A1, 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 A2, 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 so on. And you can see this because the derivatives with respect to omega and t with respect to y gave us the coefficients in terms of y. Okay, so the last thing I want to show you now is what happens when we try to integrate this. Now this is all a constant. There's nothing in any of this expression here that is a dependence on x or y. So actually the integral of this simply just becomes the integral over omega, which is just equal to area. So actually what we end up with is the integral of, say, d omega dy, dt dy, d omega is equal to a over 4a squared times, and let's just write it in matrix notation. So this would be omega I not sure what's happened here. Omega I, AI, AJ, T, J, like that. So this is just index notation. You can see these could be 1, 2, and 3. Don't worry too much if you don't like index notation, but it's just a short way of writing this. The key point here is these two cancel, and we end up with 1 over 4a. So that entire integral essentially has now just become very, very simple. Okay, so then the process proceeds exactly as it has before. Now we've actually got 3 omega coefficients, which correspond to the 3 nodes of our triangle, which means we now have 3 equations essentially for each of those omegas. So we can split that up into 3 separate equations and solve those individually. Now in terms of matrices, that's the equivalent of actually just saying, let's get rid of this omega term. And now you see we have this expression that then becomes essentially 3 equations if you're working in index notation. But rather than writing all of this out, I'll show you on the slides. Any questions about that? Does that make sense? Okay. So I know it's called mathematics, but it's conceptually, there's nothing different here from what we did before. Okay, so this is just the kind of written up form of these. We just expand the 2 equations up, and then we just collect those together. And then essentially we're just working through, and then this is just evaluating that integral over there, which just gives us this area expression there. And exactly the same thing for the y components. And so what we end up having here is basically the approximating each of those. So the next step is to put those equations together. So the third step is to collect together these equations for each of these triangles. So the full expression for a given triangle includes both these terms, includes the 2 matrices. Now these term here and here are identical for both of these, so it's only these kind of matrices of B and A components that are basically different for the x and y derivatives. So the expression for one single local triangle is basically this. So now the process is to collect that together and form a mesh for lots and lots of triangles, and then solve a set of simultaneous equations for all of those triangles. In exactly the same way, we collected together a global matrix and solved a set of simultaneous equations for individual pieces of a straight line. Now, what becomes more complicated is the node numbering. So when we were in lecture 3, I think, there was a question about the link between local and global numbering. Now, essentially, what we have is the element number on the left-hand side and then the corresponding nodes. And what you have to do is you have to keep track of, for a given element, which nodes correspond to that. The other thing you have to notice is each of these nodes is now shared by lots and lots of different elements. So within our matrix, this means that a given node will actually be contributed to by the deformation and change of each of these kind of wider range of elements. Now, in terms of your understanding, this is actually not important. The reason why we've done all of this mathematics, the reason why we've talked about it in this form, is at no point do you actually have to think through this, really. The whole point is you build up a code to do this for you. So essentially the process is kind of mechanical. You go through and you define the element table like this. Now, in terms of the computer code in Matlab, hopefully, well, you possibly wouldn't have got to question 4, but this was essentially an example of how we do that in Matlab code. So we start by defining the domain size, Lx and Ly, in this case, say 3 and 2, and we specify we want 3 nodes in X and 2 in Y. So this just basically means each element side will be 1. So our dx and our dy will be equal to 1 in each case. We're then going through and we're actually looping over and creating each of the node points in 2 dimensions. So you can see what we're essentially doing here is we're rewriting these x and y arrays where each of these is basically the index, which goes from 0 to the number of elements times dy. So this gives us each of these values. And then the count essentially puts that in a single column matrix. So we're getting each of the x and y coefficients put into that particular column. And then we define a connectivity based on that. So this tri-matrix is essentially doing the mapping that we saw on the previous slide. So for element 1, the first element of that tri-matrix, it has the indices of node 1. So that's 1, 2, and 6. And you can see here 1, 2, and 6. For element 2 of tri, that's 6, 5, and 1. And you can see that's 6, 5, and 1 in this global mapping. And then the process is one of basically plotting this. So if I open Matlab, I'll show you the grid creation in 2 dimensions. So the first thing you can do in Matlab is you can actually put breakpoints. Bear with 1 second, sorry, let me make the font bigger. Fonts. Okay, can you see it? Perfect. So okay, so we can set breakpoints. So let's have a quick look in Matlab, and this code is all available in the lab we did this morning. So I urge you to try it. But essentially, what we're doing here, if you look at the workspace, which unfortunately I don't think I can make bigger, but for element 1, 0 here and 0 here, you can see that I times dx is going to be equal to 0 and j is going to be 0. So the first element of count is going to be 0 for x and y. Then we go to I is equal to 1 now, and you can see that the I times 1 times dx will give you the value of the first node. That's node 2, if you like, and that's put into x and y, and so on. So we go through all of this process. Then we define this connectivity matrix, and then we plot it with triplot. So let me just run through. And what we see is essentially the same plot that you've just seen, and this is created now with Matlab. So one of the things you'll probably find most tricky about going from 1 dimensions, assuming you've understood the kind of process of doing 1-dimensional finite element analysis, is just keeping track of these node numberings. And this is where Matlab helps you, because you set this up and you have these kind of matrices that give you the kind of mappings between your global and local, and then you can use those to kind of essentially loop through each element and each of the nodes. Yeah, does that make sense? Any questions on that? Okay, perfect. Okay, so that's just the plot we've just seen in Matlab. Okay, so let's have a look how we now assemble the global matrix of elements. So the first element is 1, 2, and 6 in terms of the node numbering. Now, one thing to note is the node numbering is not unique. You can actually number the nodes in any way you want. There are some advantages to numbering them in a particular way. If you number them in a particular order, you'll actually get more efficient matrices to solve. And we can talk about that briefly next week. But for the purpose of this exercise, these matrices will be fairly small. It shouldn't matter too much. So okay, so the process now is we take this expression for this first element here. Now notice that B1, B2, and B6 are the elements of this matrix here. We're multiplying that by T1, T2, and T6. Okay, but the thing to note is this general triangle that's in terms of all of these, you know, B1, B2, A2, A3, actually, you think about it, it's actually only got A6, B1, A2 and B2. So those other expressions are equal to 0. So if you look at that, essentially we have B2 is equal to 1, A2 is equal to minus 1, A6 is equal to 1, B1 is equal to minus 1, and then B6 and A1 are equal to 0. So, just for the next maybe 8 or 9 minutes, go through and substitute in those values into this matrix, just to see what form you get. So the idea here is to basically use the expressions here and have a look at the form of K1 you get, just to understand actually the process of actually substituting in for this expression. And why you do this, I want you to just understand that essentially, because we've chosen a particular simple triangle of this form, it's made it simpler. So a lot of these expressions will disappear in these matrices, and you actually end up with a kind of simpler matrix. For the more general case, these will be kind of more complicated. And again, it will be on poll everywhere. You can add an answer to that. So, have we done it? Here we go. So it's just an exercise in kind of understanding the process of substituting in. The reason why we do this by hand, and you probably will never have to do this by hand again, is to understand essentially what you need to do in the Matlab code and how you build these matrices up and the code you have to write to do this. But the process here really is one of just getting an expression for this triangle. These would be more complicated matrices if you had a form of more deformed triangle. We'll talk about that a bit next week, but certainly for the exercise that we talk about, we've designed a kind of perfectly uniform lattice. Okay, so then the other thing to think about is the next triangle. This is element 2. Now if you look at this, the coefficients have changed. Now we have x1, x6 and x5. So we're sharing 2 of the same points, but we now have x5. And you can see the matrices here are slightly different. And what you notice is K2 is actually the inverse now. So the B matrix is basically the transpose. It's not quite a transpose, it's actually flipped over, reflected essentially along the middle diagonal. So if you compare those 2 expressions by flipping it over, we actually get an expression that's kind of flipped over in the A and B components. But the key thing to note is actually the form of the matrix we get for that triangle and that triangle is identical. So this right hand side is the actual form of K1, and you'll notice that K2, which is for the kind of the next triangle here, is identical. So what this means is that expression excuse me, for K is identical for every single triangle. That is, we only have to do this once because we have exactly the same triangle across that. We can do exactly the same process, and we know that the form of the stiffness matrix is identical for all of those. Now this is the same process we had when we defined, an expression for individual matrices, which were minus 2 over h on a diagonal and 1 over h off the diagonal. Exactly the same thing now here with individual components. So just in general, this is for A1, A2 and A3. You can see that you kind of add these 2 together, you get the sum expression. So let's say each triangle side is 1, so our domain is 3 by 2. So each of the elements is size 1. And essentially the process of building up a global matrix, now don't be too worried about the size of this. I mean, this is probably already bigger than what you'd want to do kind of manually, but just notice that what we're essentially doing is taking this expression here, which is for T1 and T2, and we're sticking it in here for T1 and T2, so they just correspond with that. So it's basically just putting the local part of this global matrix for all 12 nodes. We stick those elements where they go there. Let's now stick in blue. So for the T6 component, we're essentially sticking in the T6 expression, so we count 6 along in this direction. And we're putting this here. At 6, 6, we've got a 1, and at 2, 6, we have an expression. You can see these. So the reason we have them at these points is because we've actually got the 6 component interacting with the second one, 6 component interacting with the second one, and the 6 component here for that. So you put them into the global matrix. We do the same thing for element 2. That's what I did earlier. So the next step is to put in the expressions for element 2, which are 1, 5, and 6. Now, bear in mind, you're not going to do this manually. You'll end up doing this in code form. But essentially, the process is the same. You take the T1 component and stick those in, T2 components, and then the 5 and 6 components, and essentially work through. And if you do that for every single matrix, you end up with the kind of global matrix for your system. Now again, no one's expecting you to do this manually. The point is you write code that will go through and do this, following a series of rules. And these rules based on the kind of mapping between the elements, and then just the location to put them in the array. Does that make sense, just in terms of the kind of building this up? So it's the same concept you've seen before with the straight lines. It's just more complicated because we've actually got to insert elements here and there, but the process is essentially the same. Okay, so the last thing I want to talk about is surface terms. Now, I kind of just skipped over this and said they're surface terms, but when you do integration by parts, what you end up with in multiple dimensions is this surface expression on the right-hand side. Now, physically, you can think of this, process as giving you kind of fluxes over the surface here. And for a triangle, you have fluxes, in the x direction, in the y direction, and then on the diagonal term, you get both an x component and a y component from that. So, the process of surface fluxes in 1 dimensions, which is basically at the node, you get the 2 surface terms. In 2 dimensions, you get these kind of fluxes over each of the surfaces of the triangle. Now, the good news is about the diagonal term is actually you don't have to worry about that, because all of the internal diagonal terms that you have here essentially cancel out. So in the same way, in 1 dimensions, between each of the elements, the terms cancel out. In 2 dimensions, actually, the only thing we have to worry about are these expressions at the boundary. So that's it. And essentially, these are our boundary conditions that we have to define. Now, one problem is the boundary condition actually, in this particular case, has to be defined for almost every single node we've got. There's actually only 2 nodes here that we don't define the boundaries for. This is true for a very small system. This is arguably the smallest system you can do and still get interesting results. Potentially we could have cut down by this section here, but the idea now is that then you write a general code that you can expand out. But the process of setting the boundary conditions is as we did before. So the fluxes would be the right-hand side of our expression. And these fluxes would actually just be values that we specify on the right-hand side. And I'll talk a bit more about how we get these next week. And then in terms of setting the constant boundary condition, the Dirichlet boundary condition, we do the same process of essentially eliminating rows of the matrix. So in our case, if we want to eliminate, we want to set a 0 boundary condition on the top and bottom. Each of these nodes along the top, which are 9, 10, 11, 12, and 4, 8, and 12, we essentially just eliminate those rows and columns from the matrix. And we end up with a vastly reduced matrix that essentially is just for the unconstrained degrees of freedom. So the process ends up being the same as in 1 dimensions, but more complicated. And I'll talk a bit more about this next week and how we get there. And then the last thing I want to talk about, just briefly before we go away, and I'll talk about how we do this next week, is in the last 2 terms. So the exercise you're going to have to solve is going to include a coefficient here, but it's going to require you to solve essentially this expression with these 2 extra terms. Now, today we've talked about how to solve it for just these 2 equal to 0. You've now got these 2 extra terms. Now, the process we do is one of integrating this expression over omega. So we're going to end up with a term which is going to be omega t, wt times d omega. And we're going to end up with an expression for f d omega like this. So these are going to be the two extra terms we're going to need to take into account. So we've done this term already today, but we're going to need expressions for these two. Now, very briefly, the way we're going to do this is we're actually going to, this should be w times f. The way we're going to do this is we're actually going to cheat and just say, actually, this is a constant, so what we're going to end up with is something along the form of a times f. And if you think about it, that's essentially what we got when we worked through the process in 1 dimensions. We got trapezium rule that gave us h over 2, which is just the length of the line times the change in that. So essentially, this process, we can get just the area of the triangle times f. That would be the form we get of this equation. With this, if we want to solve this, and this is now the product of two shape functions, the product of two functions at both x and y. So you could multiply all of this out and you could try to integrate it. It's probably possible. It would be extremely tedious. The other possibility is you could map these to shape functions. Now, you remember before we talked about a general thing in terms of x and y, which we then map to a perfect triangle that's between 1, 0, 1, 0, 0, and 1, 0, and then we know this is just half base times height. That's one possibility as well. So we could rewrite them using shape functions. And if you remember before, we did that for 1 dimensions, and it made it easier to do the expression for omega times t in 1 dimensions. We could do exactly the same thing here. In actual fact, what we're going to do is we're going to use an expression I put at the end of the lecture notes last week. I'm just going to go on here because I'm going to make a mistake otherwise. And this is just a general relationship for a triangle. You're welcome to try and prove it. But essentially it's an expression for integrating the product of two functions. And it's written in the form of the integral over omega of a shape function 1 times a shape function 2 to the power b is equal to 2a factorial b factorial over a plus b plus 2 factorial. So one nice thing about working with triangles is, a triangle is well defined, and people have worked out all of the behaviours of a triangle and expressions for this. So essentially this process of two product of two shape functions is actually well defined. So we can actually just use this expression in order to sidestep the mathematics. But if anyone's interested in this process, then you could either try doing it directly, try it with the mapping. The mapping process will use a Jacobian that's slightly more complicated. You'll end up with a form of shape function d by dx and shape function d by dy, which will be some mapping between those two, so it's a kind of more complicated process. And in general, we'd probably have to do something like this, but for these simple constant strain triangles, this process will be how we'll get this term. So I'll talk you through those two expressions next week. And then by the time we've done that, you've got everything you need to do to do the assessment exercise. And then the idea will be that we're going to solve this equation here, which is basically includes the extra complexity of non-uniform material coefficients, and I'll talk about it briefly next week, but in principle that shouldn't be too much more. And then basically what I'll do is I'll just go over this derivation again, put in a bit more details about boundary conditions, and describe the additional terms. And then I'll have a little bit about best practice in FEA. So this will be about higher order elements, other element types, moving to 3 dimensions, and then a whole range of advice from people who've worked in industry along the lines of how to actually simplify the problem. And hopefully this will motivate for you while we're doing 2 dimensions. Generally, you should use the simplest model you possibly can, because as you may have found already, the more complexity you add in, the more things that go wrong. So use the simplest model, understand exactly what you're doing, try to model it more simply, and then use that to then validate your more complicated model. And by the way, that goes for the assessment. There will be scope for using, say, 1-dimensional models to validate your 2-dimensional, because you're 1-dimensional is simpler. The QR code and a link for that will be open for the week, so please stick on things that you want me to cover again. If there's something you're really confused about, I've covered badly, please stick it on there. And then the Matlab, I'll try and cover bits and pieces during the lab sessions. I think given the range of background, it's not a good idea in the lectures, but I'll try to put together a few bits and pieces. So again, give me some feedback on exactly what it is you'd like to see for that. And again, next week 11 for the lab, and then 2 Yeah, sorry, it's not. I don't know. I see some of you are kind of quite tired after 2 hours in the morning, but it's only this next week we'll do this, and then we just go back to having a lab session. So, hopefully easier. Yeah, and I'll be around for the next hour in my office if anyone has any questions. Feel free to stop by. Thanks.